Welcome back, guys. I'm here with you to solve this problem number 70 of CSIR NET June 2019. So this is a question from the analysis and it is of 4.75 marks. So for this question, I will say that this question is little bit tough. Okay. So in exam, you can skip these type of questions. Okay. Because this question, you cannot figure out this question in about 5 or 6 minutes. It will take much more time than that. Okay. So now I will provide you the solution. I'm providing you the solution because if you will solve this question, you will get many things from this question. Okay, you by solving this question, your knowledge, your level of knowledge will increase actually. So therefore I am solving it for you. This video can take time, but what you have to do, you have to just go with me. Okay, so don't think that this video is long because this question is typical. So in order to make you understand this question, this problem very clearly, I have to take time, right? So let us start. So it says that let x be a countable set, then which of the following are true? So the first one says that there exists a metric D. So the question firstly says that there exists a metric. So this is a very typical thing to figure out, right? You have to find a metric such that this space, metric space x comma D is complete, right? And the second one says that it is not complete, third one says it is compact, and fourth one says it is not compact. So you have to find out a metric. So you have to check whether such metric will exist or not. So these type of questions are always little bit tricky. Okay, so firstly I want to make you clear that what is the meaning of countable. Okay, so countable, this word countable has two different meaning. The first one you can take that countable actually means finite as well as countable infinite, and the second meaning that you can take that countable actually means countable infinite. Okay, so in many books the meaning of countable is taken to be countably infinite. Okay, so your answer key for this year June 2019 is has actually two answers for this question. So first answer is because of the meaning of countable. Okay, so if you will take the countable meaning to be finite as well as countably infinite, then the answer will be different, and if you will take the meaning of countable to be countably infinite, then your answer will differ, right? So what I want to say that I am solving this question by using the meaning of countable to be countable infinite, and if you will see the solution for this one, then you can figure out actually the solution for that one easily. Okay, so I will do this part only. So now let us proceed, right? So what you have to do, you have to figure out a matrix such that this matrix metric space x comma D is actually complete, right? So since your x is countably infinite, that means there will exist, okay, since your x is countably infinite, that means there will exist a function such that from x to a countable set C. For any countable set C, there will exist a function f such that f is a bijection. You are getting my point or not? Now for this bijection, I am choosing my metric. So I am choosing my metric from x cross x, right, to R given by d of x comma y is equal to fx minus fy. This is what I am choosing my metric. What is this function f? Which is which I have initially defined to be a bijection between x and c. What is c? C is a countable set, any countable set, right? So this is the metric that I am taking for this question. Okay, so firstly what you need to show is that this is actually a well defined function from x cross x to R. This is what you have to show, and the second one you have to show that this is actually a metric. So this is, I will give you exercise. Okay, so D is a metric. This is what you need to prove yourself, right? So I will show you the definition for the metric. So firstly, the metric space. What is a metric space? It says a metric space M. A metric space is an ordered pair M comma D, where M is a set and D is a metric on M. That is a function D such that M cross M which satisfies these three things. So if you somehow prove that these three things are actually true for this one, then you are done, right? So from that thing you have to prove it yourself. Okay, so this is easy thing that you can prove. So from here I can directly say that x comma D is a metric space, right? So now throughout the question I will take this to be my metric. Okay, so now I will erase this thing. Now firstly see, in your question, what you have to show in your option, first option, you have to show, I will keep this thing here for your reference. Firstly, you have to show that there exists a metric D on X such that X comma D is complete. This is what you have to show. So now firstly, C, you have to show that X comma D is actually a complete space. So in order to show some space, a complete space, I will define that thing. So suppose X is a space, metric space you can say. So if you want to show that this space is actually complete, what you have to show that if you will take Xn, a Cauchy sequence inside it, then this will imply that Xn is convergent, right? So this is the meaning of completeness. So if you want to show that X comma D is complete, then you have to show that for every Cauchy sequence inside this, you will get a for every Cauchy, not for every, I will say every Cauchy sequence inside this converges, then you are done with this thing. You are getting my point? If you want to show that X is complete, then you need to show that every Cauchy sequence inside this will converge. So I will erase this thing. This is what you have to prove. You have to prove the X comma D is complete. This is what you have to show. Now what is D? D what I have taken earlier. Okay, this is my D. So what I will do, I will take my F, the function that I have taken earlier, a function from X to this set 1 by n such that n belongs to natural number union 0. So this is the basic set that I can take. Okay, you can take any countably infinite closed set here. Okay, this set is actually countably infinite as well as this set is closed. Okay, so what I mean to say that you can choose any set here, okay, which is countably infinite as well as closed, because for that set you will get a such F such that F is bijection, right? Now I have taken my proper F. Okay, initially I was writing C here, but now my F is like this. Okay, now for this F, my definition of the metric is earlier I have defined the same metric. Okay, so now F is a bijection, right? Now what I will show you another note. So what this note says actually that if Y be a subspace of a Banach space, then Y is closed if and only if Y is complete, right? So this thing is actually a subset. Okay, this Banach space actually means completeness. Okay, it is with respect to the norm, but you can take this meaning of Banach to be complete thing here. Okay, so this thing is actually complete with respect to R and D. What is D here? D is actually the usual metric. Okay, the modulus metric that we usually take in R. So this thing is actually closed subspace of R and D. You are getting my point or not? So by using this theorem, what you can say, this thing is closed. From this thing you can directly say this is complete. So you already know that this set that I am taking is actually complete. This is what you know. Okay, now using this knowledge I will prove that X is complete. Okay, by using this thing I am proving that this is complete, right? So now let us proceed. So this is complete, you already know. Okay, this one is complete. Okay, so you need to show that X is complete, right? So I will take a Cauchy sequence inside it. Okay, as I defined earlier. So Xn be belonging to X be Cauchy. Let us say you need to show that this Xn is actually convergent. This is what you need to show. So since it is Cauchy, so by the definition of Cauchy, what do you know? That Xn Xm, distance between Xn Xm, what is D? D what I have taken earlier. Okay, so the distance between X and M is actually less than epsilon. Okay, whatever epsilon you choose for some. Okay, there okay, I will write it properly. Let us take epsilon greater than 0. Then this will imply that there exists n naught belonging to natural number such that distance of x comma n is less than epsilon for all n comma m greater than n naught. This is by the definition of Cauchy. Okay, now what is the value of dxn comma xm? The value is f of xn minus f of xm. This is the value. Okay, now in which set you are? Now you are in this set, right? What is the image of f? Fxn will lie here and fxm will lie here. So from here what you are getting, that fxn is Cauchy in where? It is Cauchy in this set, what you have taken. Now you already know that this set is complete, right, using this note. So from here you can say that fxn converges to some L. I will use L here, okay, converges to L by the definition of completeness of this space. Now since it converges to L, okay, where L belongs to this space itself, let us say this space is C, so this belongs to C, this space, this L will belongs to C. Now since F is a bijection between them, so since this is since L belongs to C, that means there exists a pre-image of it. You are getting my point or not? Using the bijection thing, what I can say, that this L is actually equal to some Fx, because F is a bijection between these two, right? So I will directly write that this Fxn will goes to some Fx where small x belongs to your capital X, right? Now see, fxn goes to fx. Now what is my claim? My claim is that this xn sequence that I have chosen earlier will actually converge to this x. So that means I want to show that xn comma x is actually less than epsilon, right? Whatever epsilon I choose. So now firstly calculate the distance between these two, okay, and so the distance between these two will be given by fxn minus fx, right? So now this fxn will go to fx, because why? Because it is given to you, because fxn goes to fx, this is given to you. So this quantity will be less than epsilon for some okay, for some n naught. So I will write for all n greater than n naught, okay. This n naught is not same as this n naught is different, okay. So from here you have concluded that xn goes to x. Finally you are done with this thing. So from here what you have finally concluded? You have finally concluded that your space is complete, right? Because you have taken a sequence which is Cauchy inside it, and now you are proving that xn goes to x. So you are done with this thing. So that means your first option is actually correct, right? Now I will show you another thing. Why I have taken this set, okay, I have to take a countable set here, okay, this is what I have defined earlier. So I have to take a countable set here. So I am choosing, this is the basic countable set which is closed. So therefore I am taking this set. You can take any other set which is countable as well as closed. You're getting my point? You can take any set that will work, okay. There is no special thing about this this set that I am choosing. So now I will erase, okay, I will erase later, but I will show firstly the option number third, okay. So option third, I am going to prove that there exists a metric D such that x comma D is compact. So with respect to this metric D, what I have chosen earlier, I will show that x comma D is also compact, okay. Now what is the definition for compactness? I will use the sequential definition for compactness. So what is the sequential definition? It says that if you will choose any xn belonging to x, any sequence inside this will imply, okay, what is the definition for compactness? I will speak it. So if you will choose any xn belonging to x, then this will imply that there exists a subsequence xnk belonging to there exists a subsequence of xnk. So there exists a subsequence xnk of xn such that xnk converges to some x naught belonging to x. This is the definition for compactness. So whenever you have to show this set is compact, what you have to show, you choose any arbitrary sequence inside it, then you need to show that it has a subsequence which converges inside this set, this x complete this space x. This is what you need to show. You are getting my point or not? So this is the definition, right? You can if you are not getting the definition completely, you can Google it, okay, and then you can figure out what is the definition. I will say sequential definition for compactness, okay. This is what you can Google and then figure out what is the definition, okay. I will repeat it again for you, that any space x is said to be compact if for every sequence inside it there exists a subsequence which converges inside this set. So this is the definition, okay. I hope you now understand. I will erase this thing now. So you need to show that x comma D is compact. So I will take an arbitrary sequence inside it. So I have taken an arbitrary sequence inside it. Now you need to show that there will exist some subsequence such that which converges, right? You need to show that. Now so you have taken an arbitrary sequence inside this thing, okay. Now this will imply fxn belongs to this set, right? Now this set is actually in R comma D space, this bigger space, right? Now what is this set? This set is actually closed, as well it is bounded. So with respect to the usual metric, this is the usual metric, okay? This metric is not same as this metric. This metric is a usual metric. So now what do you know in R space, in R comma D space, with respect to the usual metric, closed and bounded imply compact. So for this set, you know that this set is compact, right? So since this set is compact and this is an arbitrary sequence inside it, so by this thing what you can say, that there exists fxnk, a subsequence of fxn, such that fxnk goes to some fx. This is what you can say by using the definition of this set, because this is compact. So by, if you have a sequence inside it, that means you will get a subsequence such that fx and k goes to fx. I am using the compactness of this thing here, right? Now I will show that this x and k, okay, this x and k is actually a convergent, okay, this x and k is actually a subsequence of it, that you already know, that this x and k is actually a subsequence of it. You have to show that dx and k comma x, that means you need to show that x and k goes to x. This is what you need to show, okay? So this quantity is actually equal to fx and k minus fx. Now since this converges to this, that means it will be less than epsilon for all and greater than n naught. So finally you have proved that this x, for this xn you are getting a subsequence which converges to some x. Finally you have done, okay, by the definition of sequentially compact thing, you are done that x comma d is actually compact, right? So I have done third part also. So third part is now correct. Now what you need to show, you need to show for the second one that there exists a metric d on x such that x comma d is not complete. For the second part you have to show this thing, okay? Now I will erase everything. Okay, I will keep this thing here. Now what do you know, what do you need to show that this space is not complete? So for this option I will take my f to be a function from this space to this space, right? So I will take this basic set. So this set is actually countable. Now it is not closed, right? So therefore it is not complete. Now by the same metric you can actually prove that this x comma d space is not complete. You are getting my point or not? What metric do you have? You have metric like this, right? So I will leave this for you, this part and this part, fourth number part, that you can actually show by taking this as your function that this second and fourth part are incorrect. That means since this set is not complete, therefore you can show this thing that this metric space is actually not complete. You are getting my point or not? This is what you can actually show. So this is your exercise. I will give this to you because I somehow will figure out that's why this is not complete and why this is not compact. I will figure out this myself, but that will be not beneficial for you. I have done all the thing in the first and third option. I have done everything. By that thing you can actually, you have taken the idea, right? So from that idea I will suggest you to solve this option number 2 and option number 3rd, and also see that this set is not compact also. So since it is it is also not compact. So in the third option you have to use this property that since this is not complete, therefore I can show that x comma d is not compact, not complete. Now for the fourth option you also know that this is not compact. So for the fourth option you have to use the non-compactness property of this thing. So from this thing you can actually show that there exists a metric such that it is not complete as well as it is not complete as well as not compact. You are getting my point or not? I will repeat myself. I have done everything what I can do in option number 1 and 3rd. I can similarly do option number 2 and 4th, but that has no meaning unless you try it yourself. So I will suggest you to solve this 2 and 4th option by using this thing. If you will take your function to be a function from x to 1 over n, this set, and you already know that this set is not complete as well as not compact, so from that thing you can figure out it yourself that your x comma d for this function is not actually a complete as well as compact. Okay, so finally I am done with this question. So thank you.